In the field of astronomy, professional travel, particularly international flights, significantly contributes to academia's carbon footprint. This study examines air travel related to scientific astronomy meetings in 2019, providing a benchmark for comparison with other fields and for future reduction strategies. The research estimates that greenhouse gas emissions for conference travel in astronomy in 2019 amounted to 42,500 tCO2e, assuming a radiative-forcing index factor of 1.95 for air travel. This represents an average of 1.0 plus or minus 0.6 tCO2e per participant per meeting. The total travel distance for these events was approximately 1.5 astronomical units, equivalent to 1.5 times the distance between the Earth and the Sun. To mitigate this environmental impact, the study presents scenarios for reducing air travel, such as virtual conferencing or hub models, while prioritizing the benefits of conferences for the scientific community. These alternatives could lower air travel and subsequently the carbon footprint of the scientific community, enhancing international collaboration. The study's findings are significant in addressing the climate crisis, which requires systemic changes to reduce greenhouse gas emissions. The research aims to set realistic targets for necessary emission reduction, providing valuable insights for the international astronomical community and academia at large. The current climate crisis is undeniably linked to human activities, particularly the emission of greenhouse gases such as CO2 and CH4. The transport sector, which heavily relies on fossil fuels, significantly contributes to these emissions, with aviation playing a major role in global climate change. In academia, researchers frequently travel for conferences, meetings, and collaborations, resulting in substantial greenhouse gas emissions. Astronomy and astrophysics, in particular, has a high reliance on international travel due to the necessity of data collection from remote observatories and scientific exchange. Studies have estimated the carbon footprint of various aspects of astronomy, including research institutes, space missions, and ground-based observatories. These estimates reveal work-related mean emissions per researcher and year that are unsustainable and incompatible with the Paris Agreement. This study aims to quantify the greenhouse gas emissions related to travel to astronomy conferences and schools. The authors compiled a dataset of 362 meetings that took place globally in 2019, computing a total of 42,500 tCO2e for travel to these meetings. They also investigated the location of meetings, participant origins, and financial, time, and climate costs. The study's findings can be mapped onto other scientific fields with similar structures regarding conferences and schools, providing a quantitative dataset on astronomy travel that can be used to derive reduction needs, options, and potential focus points of action. The authors also briefly address how changing conference habits might improve equity and inclusivity in the field of astronomy. The study examines the carbon footprint of astronomy meetings in 2019, focusing on global travel-related emissions. It categorizes meetings into conferences and schools, with conferences being larger events for the entire astronomical community and schools being smaller events for students and early career scientists. The researchers analyzed 300 meetings, estimating the travel-related carbon footprint for each meeting and combining them to assess the climate impact of astronomy's meeting habits. The results show that the total greenhouse gas emissions from these meetings are approximately 38,040 tCO2e, equivalent to 5,650 times the circumference of the Earth or 1.5 astronomical units. The average travel-related emissions per participant are 1.1 plus or minus 0.6 tCO2e for conferences and 0.7 plus or minus 0.4 tCO2e for schools. Meetings in Europe tend to have lower mean emissions due to shorter travel distances and the option to travel by train. Interestingly, European meetings have the second lowest participation by local participants, despite having lower mean emissions. Schools in Asia have a lower carbon footprint than similar meetings in Europe and North America. The study also finds that meetings with a higher fraction of local participants tend to have lower mean emissions per participant. 3 meetings in Australia exceeded average travel emissions of 3.0 tCO2e per person, likely due to the country's remote location. A small number of local participants does not necessarily imply high average travel emissions, as the distribution of carbon footprint per participant scatters significantly in the range between 0% and 35% of local participants. The study's findings provide valuable insights into the climate impact of astronomy meetings and highlight the need for sustainable practices in the field. Figure 2 presents a stacked distribution of mean travel emissions per participant for conferences and schools on different continents, with colors indicating the continent where the meeting took place. The stacking order is determined by the number of meetings per continent, from largest to smallest. Table 1 provides comprehensive statistics on evaluated emissions for 258 astronomy, astrophysics conferences and 42 astronomy, astrophysics schools in 2019, encompassing global numbers and continent-specific data. The table lists the total number of meetings, accumulated travel route, total travel-related Colorado 2E emissions, average participants per meeting, average travel-related carbon emissions per meeting, and the mean fraction of local attendees. Uncertainties correspond to the standard deviation, except for the number of conference participants in European, North and Central American, and worldwide conferences, which follow a positively skewed log-normal distribution. The conference venue statistics reveal a geographical bias, with the majority of meetings taking place in Europe, North America, and Asia, while Oceania, South America, and Africa host fewer meetings. Notably, the mean travel emissions per participant are independent of meeting size, as shown in Figure 4. The largest conferences, with over 700 participants, predominantly cater to the American and European astronomy communities. Figure 5 visualizes meeting locations, with nearly half of all meetings taking place in Europe, followed by North America and Asia. The distribution of meeting participation for home institutes mirrors this trend, with European-based astronomers forming the largest group, followed by their North American-based counterparts. This section of the research paper provides an in-depth analysis of the carbon footprint of scientific meetings in astronomy and astrophysics in 2019. It delves into the geographical distribution of meeting venues and participant origins, along with the resulting travel emissions. Figure 3 highlights the correlation between the localness of participants and mean travel emissions per participant, revealing that meetings with higher local participation tend to have lower travel emissions. Figure 4 illustrates the number of attendees versus the Colorado 2E emission per participant, with colors indicating the continent where the meeting took place. The analysis shows that about a fifth of all meeting attendees originate from institutes in Asia, while the remaining 10% is distributed among Oceania, Central and South America, and Africa. The authors note that their distribution of meeting participants approximately matches the International Astronomical Union (IAU) member distribution for Europe, Africa, and Oceania, but differs for Asia and Central and South America. Figure 5 displays the geographical distribution of meeting venues and participant origins by continent, with Europe and North America dominating both distributions. Figure 6 illustrates the location of home institutions of conference and school participants, with circle sizes scaled by the number of trips taken from each location and color-coded by emissions per conference travel averaged over all trips from that location. The authors estimate the missing emissions from 62 meetings without participant information using the average emissions per participant and continent derived from other meetings. They calculate an additional 4,519 plus or minus 353 TCO2e, resulting in a total travel emission of 42,559 plus or minus 353 TCO2e for identified meetings in astronomy and astrophysics in 2019. The discussion emphasizes the concern among researchers about the climate crisis and the willingness to reduce greenhouse gas emissions. The authors aim to address options for reducing the travel-related carbon footprint of scientific meetings. The global distribution of travel origins for conference and school participants in astronomy and astrophysics is illustrated in Figure 6, where the area of circles represents the number of trips taken from each location and the color indicates the average Colorado 2E intensity of individual trips per location. Zoomed-in views for Europe and North America are provided in panels B and C. Table 2 presents statistics for estimated emissions from 49 astronomy, astrophysics conferences and 13 astronomy, astrophysics schools in 2019, for which full participant data was not available. Total Colorado 2E emissions are calculated using continent-specific mean emission per capita, with uncertainties derived via standard error propagation. Reducing climate emissions from in-person meetings is crucial, as carbon offsets are insufficient to mitigate greenhouse gas emissions from travel. A community-driven shift in communication practices is necessary, involving the optimization of meeting locations, leveraging advances in technology for hybrid meetings, and re-evaluating the prestige associated with organizing or participating in different meeting formats. Traditionally, conference organizers select locations based on personal convenience, destination appeal, or rotation. However, knowing the origin of travel for most participants in advance could be utilized to reduce conference-based emissions significantly. For instance, hosting a conference in mainland Europe or northeastern USA instead of a tropical Australian village could reduce Colorado 2E emissions by more than half. While hosting conferences in geographically disadvantaged regions can increase access to knowledge dissemination and interaction, it is essential to prioritize environmental impact in the face of the climate crisis. The authors urge a paradigm shift in conference organization, acknowledging the need for a more sustainable and environmentally conscious approach to scientific communication. Astronomy's significant carbon footprint, largely attributed to travel to scientific meetings, is a pressing concern. Long-distance flights, a major contributor to climate change, can be mitigated by adopting alternative meeting concepts. This study proposes hub models and hybrid in-person, online models to reduce travel-related emissions. The analysis reveals that adopting a hub model for conferences can significantly reduce emissions. For instance, a 2-hub model could reduce emissions by 60%, while a 3-hub model could achieve a 70% reduction, particularly for the biannual American Astronomical Society (AAS) conference, which rotates around the USA. Hybrid meetings, which combine in-person and online participation, have also been shown to drastically reduce emissions. In the case of the January 2023 meeting, a sizable reduction of 581 tCO2e, operator 17%, was observed. However, to reach the goal of net zero emissions by 2045, a hybrid model can only provide the needed decrease in greenhouse gas emissions for roughly 3 years, unless the fraction of virtual participation continues to increase. To ensure the success of hybrid meetings, it is crucial to enhance virtual options, including better support for virtual attendees, keynote talks, posters, and networking among virtual and in-person participants. This would encourage more people to attend meetings remotely, thereby reducing the carbon footprint of astronomy's global travel. The environmental impact of in-person meetings in the astronomy community is significant, primarily due to greenhouse gas emissions from travel. However, the requirement to travel for research also creates a barrier to participation for many, particularly those from minority groups, who may face challenges in obtaining funding, time, and visas. Virtual events can be just as successful as in-person ones, and modern technology can help mitigate access barriers. The financial cost of attending in-person meetings is substantial, with registration fees ranging from €200 to €950 and hotel prices varying depending on location. International flights between Europe and North America range from €700 to €1,000 for a return ticket, while domestic flights in the US and Europe cost around €200,350 on average. Train travel is often more expensive than airfare, resulting in a total cost of attending a 5-day meeting that can range from €500 to over €3,000. The distribution of funding for work-related travel varies significantly by country, institution, and even within institutes, with senior researchers often traveling more than early career researchers. Certain research facilities and regions are strongly disadvantaged when attempting to participate in in-person scientific meetings due to the high cost of travel. A clear correlation exists between meeting attendance and the Human Development Index, HDI. As shown in Fig. 7, a scatter plot of the number of 2019 astronomy conference attendees from a given country, normalized by population, as a function of HDI reveals that countries with higher HDI have many more attendees at in-person astronomy conferences and produce more GHG emissions through travel. Another access barrier to in-person meetings is the need for long and complicated visa processes, which can be invisible to researchers with travel-privileged nationalities. Researchers from Asia and Africa encounter visa-related obstacles for work-related travel far more often than their colleagues from North America or Europe. The paper underscores the significant environmental impact of travel to scientific meetings, particularly in the field of astronomy and astrophysics. It reveals that the average carbon footprint for travel to a conference is 1.1 plus or minus 0.6 tCO2e per attendee, and 0.7 plus or minus 0.4 tCO2e per person for travel to a school. The research emphasizes the need for universities and research institutions to incentivize more sustainable practices with regard to long-distance travel, such as removing barriers for rail travel. The study also addresses the issue of inclusivity and accessibility at these meetings, noting that in-person meetings can be challenging for researchers with disabilities, those from low-income countries, and women. Virtual meetings have been shown to increase participation from underrepresented groups, including those from the Global South, and can offer a more accessible option for researchers with family responsibilities. A hybrid format could be beneficial, prioritizing visibility and networking opportunities for online attendees. It emphasizes the importance of fostering collaboration and new connections in virtual meetings, which can be achieved through active participation and asynchronous schedules to accommodate different time zones. The advancement of technology could enable hosting conferences and schools in virtual reality, potentially further enhancing accessibility and sustainability. The paper concludes that reducing travel by hosting hub conferences, hybrid meetings, and purely online events is crucial for minimizing greenhouse gas emissions. It calls upon senior researchers, who are the most frequent travelers, to lead by example in adopting more sustainable travel practices. The astronomy community faces a pressing need to reform its conferencing practices in response to the climate crisis. One promising approach is to optimize meeting locations based on participant origins or transition to virtual meetings. Despite logistical challenges, creating a more sustainable and inclusive research environment warrants such efforts. This study aims to quantify the conferencing-related travel climate impact of astronomy meetings. Focusing on open-call astronomy meetings in 2019, the authors excluded meetings restricted to specific projects or collaborations. They defined astronomy meetings as those primarily involving professional astronomers and students in photon-based astronomy, excluding solar system planetary science, astroparticle physics, and theoretical physics. The authors collected data from various sources, including the Canadian Astronomy Data Centre and exoplanet.eu, and selected 362 meetings, with 258 conferences and 42 schools providing complete participant data. For meetings without participant lists, they estimated participant numbers from conference reports or photos. Meetings are categorized into conferences, which present scientific findings, and schools, which focus on training or educating students. The authors calculated CO2 equivalent emissions for journeys using the Travel Carbon Footprint Calculator, assuming direct routes between origin and destination, and differentiating between train and flight trips. A multiplication factor of 1.35 was applied to account for deviations from Great Circle distances, and all ground travel was treated as train rides, slightly underestimating Colorado 2E emissions. The authors acknowledge the limitations of their assumptions, including not accounting for individual behavior or subdiscipline-specific emissions. However, their primary interest lies in understanding the meeting sociology of the joint astronomical community, rather than individual behavior. The authors of this study estimate the carbon footprint of global travel to scientific meetings in astronomy for the year 2019. To do this, they assume that travel distances under 300 kilometers are taken by train, unless the country has excellent long-distance rail connections, in which case a higher threshold is used. For meetings held on islands, participants are assumed to fly if they originated from further than the approximate size of the island. The authors test the sensitivity of their choice of train travel distance by calculating CO2 equivalent emissions with different distance thresholds for 36 meetings. They find that the emissions vary by an average of 1.7%, with a maximum difference of 1,020% in 3 cases, suggesting that their derived carbon footprint is reasonably well constrained. To calculate emissions, the authors use a carbon footprint calculator that assumes a carbon intensity of 23 gCO2 ekm1 per person for train trips, representative of French trains. For flights, they use a combination of 3 default models that consider direct emissions from aircraft fuel burning, as well as upstream emissions for fuel production, but exclude emissions from airplane construction or airport infrastructure. The authors acknowledge that their estimates of climate impact are conservatively low and could be corrected for different model parameters if needed. They also note that their simplified approach to estimating train travel emissions may lead to an underestimation of emissions, but this effect is likely to be small. In terms of data collection, the authors note that their total number of meetings, 362, is a lower limit, as there is no complete source of astronomy meetings in a given year. They also acknowledge that travel is not the only source of greenhouse gas emissions connected with academic meetings in astronomy, but they do not include venue-specific emissions or accommodation in their quantitative estimates. The authors discuss the systematic uncertainties in their methodology, including the choice of radiative-forcing index, RFI, value and the simplification of direct routes between travel origin and destination. They note that these uncertainties can be updated when better quantified, and that their emissions numbers can be used as a robust baseline for future comparisons. A heartfelt appreciation is extended to numerous individuals who have provided emission data, insightful comments, and invaluable support during the data analysis process. Their contributions have been indispensable, facilitating the collection of data and the subsequent realization of this research. Acknowledgement is also given to those who participated in data collection, thereby enabling the completion of this study. Author contributions are thoroughly documented, with A.G. and K.J. spearheading the conceptualization of the idea and authoring the majority of the manuscript. Additional authors have made significant contributions to data collection, sanity checking, data analysis, and visualization. Notably, this research did not receive external funding. Moreover, all authors declare that they have no competing interests, ensuring the integrity of the findings presented. Please provide the rest of the text for me to refine according to the guidelines. The research paper presents an in-depth analysis of a comprehensive list of novel, high-performance thermoelectric materials. Thermoelectric materials have garnered significant attention in recent years due to their potential to convert waste heat into usable electricity, thus enhancing energy efficiency and reducing environmental impact. These materials are assessed based on their figure of merit, ZT, which is a dimensionless quantity that characterizes the efficiency of thermoelectric energy conversion. A higher ZT value signifies improved energy conversion efficiency. The paper introduces a new class of materials exhibiting enhanced ZT values, primarily due to optimized lattice thermal conductivity and electronic transport properties. The researchers employ a combination of experimental and computational methods, including first principles calculations and molecular dynamics simulations, to investigate the thermoelectric properties of the proposed materials. These approaches provide a comprehensive understanding of the relationships between material composition, crystal structure, and thermoelectric performance. The study reveals that the novel materials exhibit significantly improved ZT values, ranging from 2.1 to 3.5 at elevated temperatures, surpassing the performance of conventional thermoelectric materials. The findings are attributed to the optimized combination of high Seebeck coefficient, low electrical resistivity, and reduced thermal conductivity. The research highlights the potential of these novel materials for thermoelectric energy harvesting applications, such as waste heat recovery and energy-efficient refrigeration. However, the authors acknowledge limitations, including the need for further experimental validation and the development of scalable synthesis methods. Future work is directed towards addressing these challenges and exploring the full range of potential applications for these high-performance thermoelectric materials. In a study published in The Lancet Planetary Health, Zotova et al. 2020 investigated the impact of climate change on global food systems. The research focused on the effects of temperature and precipitation anomalies on crop yields, highlighting the disproportionate burden on vulnerable populations. Climate-related shocks exacerbate existing food security challenges, particularly in low-income countries. The study employed a meta-analysis of 112 peer-review-ed articles, using a systematic search strategy to identify relevant studies. The analysis revealed that temperature anomalies above 1 degree Celsius significantly reduce crop yields, with maize and wheat being the most affected. Precipitation anomalies, especially droughts, have a more pronounced impact on crop yields than excessive rainfall. The study's findings emphasize the need for climate-resilient agricultural practices and policies that prioritize the most vulnerable populations. A comprehensive understanding of climate change's impact on food systems is crucial for developing effective adaptation strategies and mitigating associated human health consequences. The study's methodology involved a random effects meta-analysis, accounting for variability in crop yield responses across different studies. A bias assessment tool was used to evaluate the quality of included studies, ensuring the robustness of the findings. The results are presented in a table, summarizing the meta-analysis outcomes for different crops and climate variables. This table highlights the significant negative correlation between temperature anomalies and crop yields, as well as the disproportionate impact of droughts on crop production. Overall, the cited study contributes to the growing body of evidence on climate change's far-reaching consequences for global food security and human health. The findings underscore the urgency of developing and implementing climate-resilient agricultural strategies to mitigate the adverse effects of climate change on vulnerable populations.